we've got about a sixth or an eighth or however that math works out, just emailing it to me. And then we've got some more submitting still on 2DS. So if you have a question on how to submit to Canvas, shoot that to me in an email, and you should be able to walk through it. It'll be easy. But it should be pretty easy. Just go to Canvas, go to Assignments, click on Homework 2 or Homework 3 or whatever it is, and just follow the steps to submit there. So that is a Canvas. Great to see everybody. Happy Thursday. Close my door here. And all right, let's get going. So this chapter was on the assumptions. So last chapter, we just assumed we had a perfect world. We assumed that we had normal distributions, both, if it's one sample, then that was normally distributed population. If there were two samples, then both were normally distributed. If there were two samples or two populations, we assumed both had normal distributions and both had equal standard deviation. That made it for a nice, perfect world. If that is the case, if we have normal distributions and equal standard deviations and independent observations, then we have the t-test is the uniformly most powerful test. Talked about power. It's the most powerful test at detecting the difference in means. I had a question on the quiz, when do I use t-test and when do I use a permutation test? If you have sufficient sample size, or you know that the, for whatever reason that these assumptions are met, you should get about the same answer either way, and the t-test is it's an easier test to run. It just makes assumptions. You don't have to do all the scrambling. But either way you win it would give you about the same p-value. Very, very close. The times when you need to use a permutation test for sure, the times when you're not looking at the difference in mean. One instance would be if that's not the statistic or the parameters that you're trying to find inference for. So we don't have the central limit theorem for a lot of statistics. We do for the difference of means and for means. So that would be one case. Another case is when you have really small sample sizes. When you have really small sample sizes, even if you know you're pulling from normal distribution, you may not think that you have a very good estimate of the mean of each population or a very good estimate of the standard deviation of each population. So you might go with a permutation test there. A caveat to that, though, is even the permutation test has low power with small sample size. So when you have small sample size, you don't have a lot of information. And just using a different method isn't just going to increase the amount of information you have with a small sample size. So even with the best time to use a permutation test really is when you have, when you're looking at a statistic that isn't the difference of means, or that isn't the difference of something that we have a central limit theorem for. And so there's just an example of that there. Something we don't know the distribution of, then build it with the normal, with the permutation test. I think someone has their, something on, make sure everybody's phone's on mute, I guess, and that'll help out with the background noise. But definitely unmute it if you have a question. So, all right. I like the beginnings here, but we're going to rock on. We're in Unit 3, so we're hopefully at this point we've got an idea of what that p-value is. We have practice doing the 6 steps. Now we're going to start adding what I call a complete analysis. We're going to look at the assumptions. We're going to state the problem, look at the assumptions, run the appropriate test, make a conclusion, and get the scope of inference. Man, we can really give a lot of clear, concise inference to people who are asking, who want to know, who don't know statistics. We're beginning to really start filling up our tool belt. So I'm going to share my screen so you guys can see each other, but I won't be able to see you, so just ring in with any comments or just speak up. And then, so I'm going to close this. I'm going to start this. All right, so this is it. Let's do it. Okay, I'm assuming everybody can see it. It says Chapter 3, a closer look at assumptions. If you can't see that, then let me know. But if I don't hear anything, I'm assuming you can. All right, so again, lots to cover, so let's do it. So here's where I want to start. When we don't have the assumptions met, that's when we're leaning on the central limit theorem. And we're really looking at the difference of means here. In fact, in the very beginning, I'm just going to fix this on a one sample test. So I'm just going to say, hey, let's do a one sample test. So we're not looking at the difference in means. We're just looking at getting inference for mu, the mean of a population, of a single population. So if that's the case, here's the way you can look at it. What we're looking at here is 100 samples. And I've got a nice app. If it's not on these PowerPoint slides, I'll put it out on our wall. This just comes from an app that I think is really cool that you can play around with, that will show you kind of what's going on. But so this is the example. What you're looking at here are 100 confidence intervals. Notice the green ones contain the true parameter. This bar here represents the true mean. And if the true mean, let's say that the true mean here is 6, that's not a 0, that's a 6. If the true mean is 6 and it's a normal distribution, when I pull an X bar, notice this is the distribution of X bars. Those little black dots are the mean of the sample. Those are X bars. If I have 100 samples, I'm going to have 100 X bars, and I can build a confidence interval around each of those. Most of the time, X bar is going to be, because it's a probability distribution, close to the mean. That's what we can see because it's higher in here. But it doesn't mean it's impossible to get it out in the tails, even if the true mean is 6. That's what you see here with this red one. Every once in a while, by random chance, that X bar, we're just going to sample abnormally large members of the population. And that mean will be abnormally large. And if it's large enough, it won't contain the true mean. Now, one more thing before we get on with it. Of course, in reality, we only pull one sample. This is the whole key. In reality, we only pull one sample. We hope it's one of these green ones. But it might be one of those red ones. And we never know. That's why we're 95, in this case, we're 95% confident that our interval contains mu. Because we know that the way we formed this interval, if I did it 100 times, 95 of them on average would contain mu and 5 of them would not. So I'm 95% confident that the one I did choose is one of the green ones and not one of the red ones. If that wasn't good enough, if I wanted to be more confident that it contained mu, I would have to make the intervals wider, right? Then I would, well, let me show you that. I'll come back to this one in a second, but let's say that I wanted to make a 99% confidence interval because I wanted to be more confident. Well, that's going to have to do this. Notice the difference, right? This guy here gets a little bigger. Because 99% confident, I'm going to multiply by a bigger number, and boom. This one was still far enough away that it didn't contain mu. So I'm 99% confident that the interval that I chose actually contains mu. However, my interval's wider. So that's the trade-off. I have more plausible values that it could be. So I think my interval is less precise. Okay, so now let's blend that in again with what a hypothesis test is. You can look at the same idea with a hypothesis test. We know that for 95% confidence, that always corresponds to an alpha 0.05 test. And if it's two-tailed, that alpha 0.05 is 0.025 in this end and 0.025 in that end. If the confidence interval, this is why they're linked, there's a one-to-one correspondence. For the confidence intervals that don't contain mu, the hypothesis test will reject the null, which is saying the exact same thing, right? 6 is not a plausible value in this red interval right here. 6 is not a plausible value. So when I do the hypothesis test of mu equals 6, I reject it because this guy is in the rejection region. And you can tell because the critical value here is the same as the multiplier of this test. This critical value is the same as the multiplier of this confidence interval. Sorry, this confidence interval. Since that's it, they're perfectly calibrated so that anything beyond this critical value, when I make a confidence interval out of it, won't contain mu. Notice this one. This one's way into the critical region, and it's no coincidence that it's way out of the intervals, not even close to containing mu. This one was really close to containing mu, and it barely rejected. This one barely rejected, a little bit more, and it's a little bit closer. You get the idea. Now, when I make it for alpha 0.01, remember, these critical values are going to get wider. It's going to be harder to reject, right? That's going to be 0.005 over here and 0.005 over here. Just like that. It becomes harder to reject. So notice what ends up happening, right? You can see all these guys in here. Boom, that's the reject and fail to reject line. Now, all of a sudden, this line is going to go out beyond. It's going to now grab this mu, or this x bar, and it'll make the interval wider because this critical value is bigger, and that's the multiplier. Really have to, kind of play with the formulas. It's not too tough to understand that idea, but that is the big idea. 99% confidence intervals will always agree with alpha 0.01 two-sided tests. 95% confidence intervals will always agree with alpha 0.05 two-sided tests. Okay, so the takeaway, confidence intervals are equivalent to hypothesis tests that have alpha level of significance. That's for two-sided tests and two-sided confidence intervals. Equivalent here means that if we test any specific value in the interval, the test will fail to reject. Means if we test any specific, right. So if you pick any value in that interval and you tested that, HO, mu equals any value in the interval, we're going to fail to reject that because it's a plausible value. And any interval outside of that, so if our interval went from 3 to 5, if we tested 6, mu equals 6 versus mu not equal to 6, it would reject. Any value outside will reject. Any value inside the confidence interval will fail to reject if it's the appropriate confidence interval. So as an example, 95% confidence intervals are equivalent to alpha 0.05 tests. 98% confidence intervals are equivalent to alpha 0.02 tests. 99% confidence intervals are equivalent to alpha 0.01 tests. So let's look at this from a different point of view. This is one that we've done before. Notice this is the Beachcomber example, mu equals 21 versus mu not equal to 21. And we said, hey, yes.
Hey, Vivian, can you let me back in the meeting? I think I got logged out. I can't see anything.
Okay. Was that Shelton?
Yeah.
Yeah. Okay. You should be back in now.
All right. Thanks.
Pretty good. Yeah. No problem. Sorry.
Yeah.
So here we looked at some data, and the test statistic was 3.31. Look at that. We rejected, right? Boom. Small p-value. We're going to reject. So question U is, will 21 be in the confidence interval? Because I'm going to end up taking this 3.31, really the value here, and building a confidence interval around it. Notice that the corresponding confidence interval did not contain 21. No surprise. Conversely, if I would put 30, if I make this mu equals 30 and mu not equal to 30, and ran with the same data, this test would fail to reject. This p-value would be much bigger. You can play around with that, but any value, if I replace 21 with any value in this interval, we'd fail to reject. If I pick any value outside this interval, I'll reject. Okay, great. I just really want to hammer that in because that's a big idea. So we've seen that before. We've seen this slide. That's okay. Oh, well, I guess I'll show this. So just to show that, this was for 21. When mu is 21, notice our confidence interval here is 23 to 36. For 21, I rejected. So I'm looking down here in this p-value. Now let's go to 22. If I tested 22, 22 is outside the interval, and notice I rejected. But my p-value is a little bigger. I didn't reject by as much. Now I'm doing 37. 37 is outside the interval, but just barely. Notice my p-value is getting bigger. I'm still rejecting, but not with as much oomph. And then finally, let me check one that's in the interval. Notice 31 is in the interval. It is a plausible value. If I check 31, notice the p-value is very big now. Under the assumption that mu is 21, this would happen all the time. This would be significant. So, so anything in the interval, I'm going to fail to reject. Anything outside the interval, I'm going to reject. Great. So,
Dr. Sadler?
Yes.
When you say it'll happen all the time, will it happen, do you mean it's going to happen statistically 68% of the time based on the p-value? For the example 31.
No, well, we're fixing the data here. So we're saying we took a sample, and now if we're, with this sample, we build a confidence interval from the sample.
Sure.
And this is the interval from that very sample. And if I was testing mu equals 31, remember x bar, what was x bar? X bar is 29.
Sure.
Right, and all of these right here, that's all 29, because I'm all with the same data. So we're kind of looking at it from a fixed data point of view. But with that data, if I switch what I'm checking I'm just showing the one-to-one correspondence. This 68.43 says if mu really is 31, right? So see the difference in what I'm saying here. I'm not going to, when I'm interpreting the 68.43 or 68.43% or 0.6843, I'm taking it from the, I'm saying 68% of samples that I take. If mu really is 21, 68% of the time, those samples will have a mean as extreme or more extreme than 29.85.
Thank you.
Cool. Awesome. But from here, I'm just saying, hey, I'm fixing my data, and I'm saying if I would start testing different things in here, you know, the last one I'll show you, look at this 23.2. That's almost in this interval, but it's just outside. And so since it's outside the interval, it would fail, it would reject, but just barely reject. And all I'm showing here is just the correspondence, the one-to-one correspondence between confidence intervals and hypothesis tests. And that'll, but anyway, we'll continue on that track. If you feel like got that, this is just kind of saying the same thing here. So we can evaluate, the whole point here is so that we can understand those plots in the book. That's what I want to really underline here. That's why I spent so much time on it, is if a confidence interval, if a corresponding confidence interval does not contain mu, we know the test would have rejected. And if a confidence interval does contain mu, then we know that that test would have failed to reject. So, anytime, so when I'm trying to evaluate tests, I can evaluate confidence intervals instead, and it's a one-to-one correspondence. So I'm doing the same thing. When you're looking at those examples from the book and in the videos, they gave evidence of these assumptions by looking at confidence intervals, not by looking at hypothesis tests, but they're the same thing. So okay, so assumptions of one sample t-test. How can we do this by hand, or how can we do this in practice? We know we have these two assumptions. Is the test robust to these two assumptions? Let's see how we know. So the two assumptions are normally distributed population and observations are independent. We're going to assume the second one. In the office hours or today, we might, anybody that asked about the cluster serial effects, that's not the real focus of this chapter. They threw it in here, and I replied to all the, to everybody that mentioned something about that in the quizzes. But we're definitely covering that more next semester, and I could bring it up in office hours. Not the super point of what's going on here, because we're just assuming things are independent right now. When the original population distribution is not normal, which is breaking the assumptions, the one sample t-test is still valid, meaning it's robust with large enough sample size because of the central limit theorem. I don't care what the x's distribution are, as long as the x bar distribution is normally distributed, because that's how I'm forming my t statistic and my p-value. That is, the one sample t-test is robust in normality when the sample size is large enough. Why does it be large enough? Why does that have to be large enough? Because of the central limit theorem. So let's say this one. This is an exponential distribution. Its parameter is lambda. But this is what it looks like. For lambda equals 1, it's a super right skewed distribution. Very not normal. Let's pretend that's the population. This thing has a mean. Depending on how I parameterize it, the mean is lambda. So the mean is 1. So if I pull from that distribution, so let's look at what we're dealing with here. And you can go to this website. I'm surprised I didn't put that on there. I will put this website on the, if I don't see it in here somewhere, I'll put it on the wall so you can mess around with this. But you say means. I want to look at means. I want to start with an exponential distribution. I want mu to be 1. And that tells this thing to pull from an exponential distribution. So what you're looking at right here in this blue was the last sample it drew. No surprise. It drew something out here because it's not unlikely to draw something. It drew from a right skewed distribution. Now, I told it to sample to make 1,000 intervals. That means it took 1,000 samples, each of size 10, and built a confidence interval from that. But it built it from draws from an exponential right skewed distribution. Fantastic. So what does that mean? Look at the intervals. The intervals, that's the true mean. Right here, 1. Right? We set that right there. Mu is 1. Oops. Sorry. So the mean is 1. Look, the intervals are right skewed. The intervals are short over here and long over here. And why is that? That is because look at the look at this here is the distribution of the sample means. So this is the last sample, and from this last sample I had a mean. That's one of the means in this guy. Notice that the distribution of sample means is not normally distributed. It's somewhat right skewed. Still, why is it right skewed? Because I've only sampled 10. That wasn't enough to overcome the right skew of the population. For the sample size wasn't big enough. And when the sample size isn't big enough, we get these confidence intervals that miss the true mean higher. But, you know, it'll hardly ever miss it high, and it'll miss it sometimes. It'll hardly ever miss it low. It'll mostly miss it high. Notice all the red ones are mostly on this side. And notice there's a couple that are on this side. And you can see that down here too. So let's see what happens now when I look at what happens in my sample size now. So when my sample size here N gets bigger, oh, and you can see that down here too. Intervals containing mu, 89.5%. This is the point. I formed 95% confidence intervals, but my intervals only contained mu 89% of the time. That's a problem. You can't report a 95% confidence interval and not achieve that. That's misleading, right? Everybody thinks that these intervals are just wide enough to hold it 95% of the time when you're only 89% confident that it contains mu, because only 89.5% of them contained it. We want the true, this is called the coverage probability, and this is the nominal percent. That's the nominal level. We want those to be the same. So notice what happens when I then sample 100 and let the central limit theorem kick in. So look at this value and then look at this value. Shazam! Now 95 becomes about almost 95, 94.3. It's a lot better. And that's because these guys are still a little right skewed, even at 100, because the original population was so right skewed. But it's a lot better. And if I made this sample 1,000, if you could afford that, then these would be even better. That would be almost 95%, and these would be just about normally distributed. There's, again, our last sample. The sample's right skewed, but the X bars are more normal. And the more normal it gets, the better this conforms to 94.3. Okay, so given the data, how can we check the normality assumption? Because obviously it's important. We only get one look at the data. There's n equals 100. What I'm showing you here is, I got a lot of confusion from this last time. You're not going to ever need to run this data right here unless you just want to mess around with simulation. All this did was simulate from a normal distribution. So what I'm showing you is 100 draws from a normal distribution. And it's just this, my point here is that even if I pull from a normal distribution, you might get something that looks a little bit right skewed like this. It's just sampling error. So your point is this evidence, given what you know now, is this evidence against a normal distribution? And you'd say no, because now you've seen that this is possible. Now, if you had an outlier way out here or way out there, that would happen very rarely if you were pulling from a normal distribution, and that would be evidence against a normal distribution. Finding big outliers or multimodal histograms is evidence against it. This isn't much evidence against it, even though it looks right skewed. It can happen. Here's your QQ plot. Doesn't look too bad at all, actually. So, so this might look a little right skewed, but this one's showing at 100 that we're pretty darn close. That's why we want to look at it. Now notice this. Oh, so what is a QQ plot? I get that a lot. I think this might be bonus on your homework. All a QQ plot is, I'll go back here, is comparing the relative standing of the observations in the sample against what that relative standing would be if they were normally distributed. And the relative standing is measured by a z-score. And remember, the z-score is nothing more than the number of standard deviations away from the mean. A z-score of 2 means the value is 2 standard deviations away from the mean. A z-score of 3 means that particular observation is very extreme. A z-score of 10 would be it's super extreme. A z-score of 0 would mean that it was the mean. It was exactly the mean, because it's 0 standard deviations away from the mean, from itself. So what this is when we say I've got this data, does this seem like this would be from a normal distribution? Well, then what you would say would be, oh, okay, let's take the x bar from here. That's my best guess of the mean. Let's take x bar and let's take s. And let's do 41 minus x bar divided by s. That'll standardize this guy. Let's do 76 minus x bar divided by s. That'll give me a z-score. And that's exactly what these numbers are right here. So you can do this in Excel and do this exact same thing. That's where I did it. So this number here is 41.2 minus the mean divided by S that you can find here. And that's saying the mean was bigger than 41.2, so that gave me a negative z-score. And this one, I don't know, I should have put the mean on here. It would have been more descriptive, but you can see the mean here looks like about 80, maybe 80 or 90 or something. So this one's below the mean, that one's below the mean, this one's about a little bit bigger than the mean, this one's way bigger than the mean, this one's the biggest from the mean, of course, because they're in order. But now what we're going to do, these are the sample z-scores. Are these spaced out about how we would expect them to be if they were normally distributed? So all I'm going to do is compare these z-scores with the ones that I would expect from a normal distribution. So before I get over here to what these guys are, which is very easy, if you only have 5, right, break them into fifths. You're going to break the distribution into fifths. So first 20%, 20 to 40, 40 to 60, 60 to 80, and 80 to 100. Right? That would be breaking the distribution into fifths. And then I want to take the midpoint of each of those divisions. So the first one is from 0 to 20. The middle of that is 10%. So I'm going to find the 10th percentile of the normal distribution. That's negative 1.28. That should be pretty close to this guy. This guy we think should be about pretty close to the 10th percentile. If it's normally distributed, it should compare nicely to the 10th percentile because that's the middle of the first 20%. Why 20%? Because 100 divided by 5 is 20. So the next one, right, this should represent the first 20%, right in the middle is 10%. This should represent 20 to 40. The middle of that's 30%. So I'm going to go look up the z-score. How many standard deviations away separates the bottom 30% from the top 70? That's about negative 0.5. How does that compare to this one? Pretty well, it looks like. The next one, this one here is the median. So that should be pretty close in a normal distribution, which is symmetric. That should be pretty close to the mean. Should be pretty close to the center of the distribution. And exactly, we would expect it to be 0. That's the z-score for the mean, for the median. And here, that one's pretty close to 0. You get the idea. This one is the 60 to 80, so that's the 70th percentile right in the middle. That's 0.5. That's about 0.7. Those are all pretty close. This one's kind of underestimating it a little bit. But then we plot them against each other, and they should line up on a line. They should line up on a line. So that's what you're looking at here. The only difference is, in most cases, these are called the sample quartiles, and these are the theoretical quartiles. These often won't be on a scale from -3 to 3. They'll be on the scale of the original distribution. I'll show you that here in a second. But the whole point is, do they line up on a line, which means that they agree with the normal distribution. And you can have QQ plots for other distributions, but we want this normal distribution. That's our assumption, so we're going to use a QQ plot. We're going to get these z-scores using a normal distribution. So these are all from a normal distribution. They're going to line up almost directly on it. The less you sample, the more it can deviate from that, but you got to remember that. If you sample a ton, look at those. Those are like almost directly on there. So there we go. How about from a right skewed? Notice here, I called it data normal, but I pulled my draws from a chi-square distribution. Now I'm not pulling from a normal distribution, and I pulled 100 times, and look at that right skew. I would not expect this from a normal distribution, this much right skew, and look at that QQ plot. It bows down. That's indication of a right skew. So all I'm doing is showing you here, hey, in real life, we're not going to know what population this came from. But for now, let's practice knowing what things could look like if we did know if it came from normal or from right skew distribution or whatever distribution. Okay, how about this one? This one I pulled from a normal distribution, but I only pulled 15. Does that look normal? Not really, but I only pulled 15. And the QQ plot kind of looks like this. But I know that it came from a normal distribution. Again, you're never going to have to run this. I'm not going to ask you any questions to run this. The only reason I have this code on here is so you can see that I pulled from a normal distribution, and these are the things I can expect. This one I pulled from a chi-squared again, only 15. You can kind of see that bowing of the QQ plot. The problem is, here's the problem, is that even at n equals 15, I could get this easily from a normal distribution. I mean, there's not a lot of difference between these two QQ plots. It's because we don't have much data. In this case, you might decide to run a non-parametric test, or you might decide to run a permutation test instead, because we may not be pulling from a normal distribution. And in fact, we weren't here. So, okay. Obviously, we can keep playing with this all day. But beware of small sample sizes. This one here, look, it's pulled from a normal distribution, but it gave me this weird looking histogram. It wouldn't do that if I pulled 150, but I pulled 15, and, you know, you're only as good as your data. So, so here's a little way to think about it. Little to no evidence against normality. You have small sample sizes, you may want to be cautious, conservative. And if you have large, so run a non-parametric test or permutation test. If you have large sample sizes and there's little to no evidence against normality, run the t-test. You're going to have the central limit theorem if it's not normal, and if it is, you shouldn't have a problem. If you have significant evidence against normality, meaning your QQ plot is really nonlinear, or you've got this big outlier in your histogram, which will also affect your QQ plot. If you have small sample sizes, you better go with something else. But if you have large enough sample sizes, no problem. It should be robust to that assumption. I'm really hammering this home on these assumptions. If you have any questions, let me know. But this central limit theorem could bail you out of the normality assumption. So
how large is large?
Yeah, and so that's variable, right? And that's the art of statistics. So how large is large? The textbooks will say 30. Sometimes 30 is not enough. Let's go back here. Sometimes 100 is not enough, right? Here, clearly 10 wasn't enough. The more skewed the distribution you're pulling from, the bigger your sample size needs to be. So, so you've got to really just look at, if you really want to get it right, you've got to assume some skewness, and you could run these simulations to see how big is big enough. If you think you're pulling from a chi-squared 3 distribution, this right skewed distribution here, let me get to it. If you think you're pulling from this distribution, right, you can run some simulations to see how big your sample size needs to be to get normally distributed X-bars. And people just throw in there 30, but sometimes it could be way less than 30 if it's not a big departure from normality. And again, from here, at even 100, it wasn't enough to give you nominally. It's very close, and usually that's probably close enough. But even at 100, it's not perfect. It's more approximately normal, but it's not approximately normal. So at 1,000, you should be doing pretty well. So I hate to give a wishy-washy answer on that. 30 is the one in the textbook, but that's a very 101, Stat 101 answer. The further departure from normality, the higher your sample size needs to be, and you got to feel that out.
Thank you.
Yeah, no problem. I wish, as a mathematician, I wish there was a more black and white answer. But by the same token, that's what kind of makes it fun. Okay, so I'll give you a complete analysis. In your homework, I'll ask for a complete analysis. If I just ask for one part of it, just give me the part. If I ask for a complete analysis, this is what I mean. Statement of the problem. It's going to help you make a really good report. You want to state the question of interest or more. Sometimes there's more than one, especially when we hit regression. Right now, we're not in regression. You're just going to state the problem. I'll show you an example of that here in a second. You're going to address the assumptions, perform the appropriate test, 5 steps. That's the 6-step test. The 6th one is the conclusion, which I'll show you another example of here. But you could call this the one, perform the appropriate 6 steps, or sometimes I break step 6 out, and then give the scope of inference, and you're done. So you've seen this example before. It is the beachcomber. Let's see what it looks like from a full analysis. So problem statement. Test the claim that the mean age of beachcomber patrons at 7 p.m. is greater than 21. Okay, I know what I'm doing now. Now let's state the assumptions. I went and took a sample. I got this. Given what we showed before, it's a very small sample size, right? The sample size is 7. That could be a chi-squared 3. It could be an exponential maybe. It could be normal. I don't know. I don't really have a big idea. If I know from a previous study or somebody told me that these ages are normally distributed going in, then I can use that information. What did I say here? Judging from the histogram and QQ plots, there's little to no evidence that the population distribution of patron ages at the Comer are not normal. I don't see any outliers in here. So if there's something popped up way out here, I wouldn't expect that in a small sample of 7, and that would be evidence against it. But they're all clustered in here. So we'll assume that the distribution is normal and proceed. I'd say it's at 7, at 7, sample size of 7, that's pretty risky. And we'll have more tests in Unit 7 to fall back on. But for right now, that's where I'm going. Independence, we'll assume that they're independent. We made a random sample at a certain time. We'll assume these are independent for now. We always want to remember that assumption. So we've already been through this a million times. So here is step 6. We're going to do we've done the assumptions. Now we're ready to run the test. Here's our test, and here is our step 6 that we've been through before, and here's our scope of inference. It was a random sample, so we can make inference to the population, and this wasn't a 2-sample test. There's no cause and effect here, right? There's no control and there's only one population. So we can assume that if we took another sample of size 7, that we would get a similar result that we would reject. We can assume that the true mu of this population is actually greater than 21. I'm going to skip this example, although I think that's a really cool picture. I think this was on your homework assignment anyway, but that is the world's smallest animal. That's crazy. That is a bat. Okay, so moving on through that. Let's go to assumptions of 1 and 2 sample tests. Yeah, I don't know why I did that. This is the assumptions of 2 sample tests. I need to fix that. This is assumptions of the 2 sample tests. Samples are drawn normally from a normally distributed population. Well, okay. If it is a 2 sample test, both populations are assumed to have the same standard deviation, and we're assuming that from every population, both populations, that they're independent, that they're independent of one another. Independent draws from each distribution. So, okay, so here's the big picture. What happens if the normality assumption is broken? That's what we want to know. We've already discussed this. If we sample big enough, and that's a good point, how large is large enough? But if we do sample large enough, and the more, this looks pretty darn right skewed, so this one might need way more than 30. This one looks less right skewed, but still pretty right skewed. I'd say we need more than 30 here too. Again, you'd run a simulation if you had an idea of you wanted to try a couple of hypothesized distributions. You could look at and draw a bunch of samples, look at the distribution of those means. But this is the big idea is, look, the X bars will be normally distributed if you sample big enough, or they'll be approximately normally distributed. With the same, this as a mu of 1. This is mu 1. Not a mu of 1. This one has mu 1. This one has mu 2. The beauty is that these means will be exactly the means of their parent population. I say parent, the population of the X's that they came from, that these X bars came from. That's why we like X bar, unbiased estimator of mu. Okay, so now we're here. Now we can understand these. Notice that these are the percentages of 95% confidence intervals from 1,000 computer simulations. That's just like what I showed you at the beginning. So they said, hey, let's pull 1,000 times from this distribution. I know it's right skewed. They pulled 1,000 times. At a sample size of 5, they're 95% confidence intervals. Those are calibrated perfectly. They're using an alpha 0.025 critical value on each side for its multiplier. Look at that. I have 95% confidence intervals, and it said it contained the mean 95.5% of the time in a sample of 1,000. That's pretty darn good. Even at sample size 5 with this much right skew, it looks like they're okay. For moderately skewed, of course, it's going to do about as well. For things that look even more normal, just about as well, even better. For things that are long-tailed, right, things that are populations that have real, that can get these really extreme values, notice that it's not good. Right? These are 95% confidence intervals, but they're way too wide. They're containing mu too many times. And you can see how people would make a mistake. If they wanted a 95% confidence interval and they were really getting a wider confidence interval, they would potentially be making the wrong decisions a higher percentage of the time. So this is short-tailed there, no problem. So these are hypothesized distributions. These are sample sizes. Notice even a sample size of 100 wasn't enough to overcome extremely long-tailed distributions. And those are distributions that have significant probability way far away from the mean. Okay, so let's keep going. All this is showing here is that most situations, normality, the t-test is robust to normality. So let's look at the second one. So if the 2 samples, both populations are assumed to have the same standard deviation, so this is our assumption. And we're assuming sigma 1 equals sigma 2. We want inference on the difference of those 2 populations. That's what group we're in right now. These 2 look like they have the same standard deviation, right? They're about the same width. But what happens if we got a histogram like that? would that be evidence for or against this population and this population having the same standard deviation? And obviously from here, this is strong visual evidence against equal standard deviations. Look at the box plot. This box plot is very narrow. This box plot is very wide. It tells me it's got higher probability of getting things out here this far away, and this one has lower probability of getting these far away. That means this distribution is it has a smaller standard deviation than this one. We don't know that for sure, but that's what this evidence is suggesting. So what about this distribution? Okay, no problem. Obviously, those look a lot better. This one looks a little less skewed. This one looks a little normal, but we've already said I got to look at the sample sizes in here that I didn't give you. But this could happen if the sample sizes are small. This could happen from a normal distribution. Certainly, that's not a lot of evidence against extremely different standard deviations. And again, there's levels, there's strength of violations. So this one I wouldn't be so worried about. I don't know if Dr. McGee said this in her videos or not, but it's a rule that she likes, and it's a rule that's been proven in white papers, maybe not proven, but highly suggested in white papers, journal articles, is the visual, you should look at it visually. And if in visual evidence you think they look the same, then assume they're the same and move on. If any part of it you're like, I don't know, I'm not sure, then just assume they're different, because we have other tests that are robust to different standard deviations. Don't run the pure t-test if you think they're different. Now, I like to look at it from both points of view so you can communicate with anybody. There are hypothesis tests that I'll show you here in a second to test. We can test the difference in means. There are other hypothesis tests that can test the difference in variances. But it's just generally bad practice to test the assumptions of one hypothesis test with another hypothesis test. Because remember, both of them can make type 1 errors. Both of them can tell you there's a difference when there really isn't. And so if you're making an assumption of the t-test with an assumption of what's the f-test for equal variances, that makes your alpha of your t-test not really 0.05, because it's depending on something behind the scenes that can also be wrong. Okay, so here's the f-test though. So you'll see this. I'll recommend, I guess, both, and you can go either way. But a safe way to do it is say, these distributions don't look like there's a lot of evidence against standard deviations. There's not a lot of evidence against equal standard deviations, so we'll assume as if they're equal and move on. But if you wanted some secondary evidence, you could go to the f-test. This is default output of proc t-test. You'll see this every time. A quality of variances f-test. Notice that this is HO's population variances are equal. Sigma 1 equals sigma 2. HA's population variances are not equal. Sigma 1 is not equal to sigma 2. Here I failed to reject, so there's not enough evidence to say they're different. Remember, this is not saying that the evidence suggests they're equal. It's saying there's not enough evidence to suggest the alternative that they're different. Very important point there. And I must have switched this table here. This should be 0.1043. Either way, you're going to fail to reject, but I need to fix that. Either this needs to be 0.4289 or this needs to be 0.1043. Not sure that happened. So I got to fix that. But either way, they failed to reject. Now, one big step here is that this test has assumptions of its own. So now we're compounding it, and that's why people don't like to use, in general, hypothesis tests to test assumptions of other hypothesis tests. This test requires you to have normal distributions. It will only test the variances of draws from normal distributions. Later I'll give you a test that's robust to that, but this test you can only use if you have normal distributions. You couldn't use it to test this, because these are pretty clearly not coming from normal distributions. Okay, just my 2 cents on that. So for this one, there's not a lot of evidence against normality, so run it. Oh, there's my 0.4289. So there's where it came from. So I just need to fix that one on the last screen. But here, both failed to reject. There's not enough evidence to say they're not equal, so proceed as if they are. This is where I say it. Couldn't use it for this one. The f-test has a strong assumption that the two populations that it's pulling from are not, must be normal. This is heavy evidence against normality. Can't use the f-test here. Later I'll show you a test you could use if you wanted secondary evidence. I hope that's making sense. I'm talking really fast here. How are we doing? Does anybody have any questions? We're hiking up a mountain. This is where we're going to stop, kind of look over the horizon and take in a deep breath and talk to other hikers. I saw a question popped up here. Hopefully Justin got back in the room. What do you guys think? I can come back out of this. I'll just come back in here. Make sure everybody's still here. That would made me sad if I came back and the room was empty. But it's all right. What do you guys think? So far, so good. Any questions? All right. Okay, these are important. Go ahead. Sorry.
Say all good.
Oh, all good. All right. Well, we'll take a sip.
Are we going to get to? Are we going to go into like examples? I guess after this, like actual like step-by-step examples.
I'm about to go into one right now. So the things I want to get done.
All right, cool.
I want to get to today. Yeah, I'm going to show you an example. 2 tests testing the assumptions. And then we're going to go into where the assumptions are broken and we might need a log transformation. I had a question on the quiz and I usually show this anyway. I'm going to show you a quick proof of why the log transformation is on the ratio of the medians and not on the difference of the means. So you probably saw that and read that. I'll make that clear. And I had a breakout. Probably won't get to it, but I'll introduce you to it. And you can do that one on your own. And I have the answers to that in the slides. So those are the big things we want to hit up. So let's get to it. It'll be great. So here comes an example. I think it's like right around the corner. But we have laid the groundwork here so that we know why we're making these decisions. So let's do it. Yeah, sorry, we got a couple more slides, but we'll get right there. So what happens if the assumptions of equal variance are broken? This is where the other plot comes in. In some sense, it could be serious, but in others, no problem. So you have this plot now. This is, again, 1,000 confidence intervals, which, remember, is also testing 1,000 hypothesis tests because it's a one-to-one correspondence between confidence intervals and hypothesis tests. So what you're looking at here is, let's just start with this one. What happens if we are pulling from normal distributions with equal standard deviations? I'm right here in the middle. Notice this is the draw from population 1. If I only pull 10 from one and 10 from the other one, so I'm pulling 10 from this distribution and 10 from that distribution. That's pretty small sample size. If I pull from those, meaning, and they have the same standard deviation, that means the ratio of their standard deviations would be 1. And notice, no matter what my sample size is, even if they're unbalanced, my confidence intervals are pretty close to 95%, right? Even if they're unbalanced, and that's going to be important here in just a second. Even if they're unbalanced, those are pretty close to 95, no problem. Now what happens, let's go to the extreme. What happens if I'm pulling from really different standard deviations? Population 1 has 4 times the standard deviation of population 2. You can see here, population 2 over population 1 is 1/4. This one is 4 times that one. That's a pretty big difference. Notice if I have the same, this is amazing, if I have the same sample size, I'm robust. My t-test is robust to that. I'm still going to reject, and my confidence intervals are going to not contain mu about the right nominal amount. About 5% are going to miss it, and about 5% of the time my test is going to reject when it shouldn't. But notice what happens when you don't have this to this extreme and we have unbalanced samples. These are way too narrow. We think we have this nice tight confidence interval that contains the mean 95% of the time, when really it misses it 17% of the time. It's too narrow. This one's really narrow, and it's because this is more unbalanced. Notice what happens when we have balance, back to good. When we get to unbalanced, back to bad. And I'll let you go from there, right? If you go the other way, if now I'm pulling more, right, N2 is either the same or more. If now I'm pulling more from the bigger standard deviation, then my intervals get wider. If I'm pulling more from the smaller standard deviations, right, I'm pulling more here from N2, then my confidence intervals are too narrow, and these are way too wide. And with decreasing a violation of that, with decreasing violations of that assumption, you have less circumstances, but still pretty bad. And so the be-all, end-all here is when your sample sizes are the same, you're robust to most differences of standard deviations if your sample sizes are the same. If your sample sizes are different, then you've got to worry about it. Turns out we're going to have a test that'll help us out with that, but the pure t-test The pooled two-sample t-test is not your test. If you have reason to believe different standard deviations and you know that your sample sizes are different. Okay, so that's the takeaway. But what you find in practice will not fit directly into one of these scenarios. You got to feel it out, and you're already starting to see, where it's robust and where it's not. That's the art. I'll let you read through these, but it's very important that you read through those. But those things we've just covered. That's when we are robust. So here we go. Complete analysis. Statement of the problem. Address the assumptions. Perform the appropriate tests. Step 6. Scope of inference. We've already done the creativity study, but we haven't looked at it from the assumptions. I've only showed you the 6 steps. I'm doing this one again because we don't want to go through all the 6 steps because you're familiar with those. But when is it appropriate to do the 6 steps? So right here, we want to state the problem. We would like to test the claim that the mean score of the intrinsic group is different than that of the extrinsic group. And furthermore, we would like to have evidence if they are different, which one's bigger. So we could have written that into the statement of problem. Next step, check the assumptions. So we go and look at QQ plots. I don't see a problem here with these QQ plots. Do you? This one's less normal looking, but let's go look at the histograms. Histograms, maybe this one's a little more left skewed. I'm not too worried about it. Keeping in mind relative small sample sizes. One was 24, the other one was 23. These aren't too far from normal, so I think that even at 24 and 23, that would be enough to invoke the central limit theorem because there's not too far to go if they're not normal already. So visual inspection and histograms are consistent with normal distributions. We'll assume normality and move on to the second assumption. That's how you could write it. Again, this is one of those instances where as soon as we get into chapter 4, you'll have alternatives, and you can, various different people will make different decisions. As long as you make the decision for the right reason, you can be correct. If I run the t-test and you run a rank sum test, which you'll learn next class, that's okay, as long as you defend your assumptions. So we check the assumptions of normality. How about equal standard deviation? So I'm looking at that. I'm doing the visual. I would be fine with the visual. A visual check was done. It reveals similar shape and supports equal variance assumption. You can assume equal variances here. But if you wanted the secondary evidence, because these aren't too far from normal, if they're far from normal at all, not a lot of evidence against normality, so run the F-test. That F-test fails to reject, so they agree. This is secondary evidence. If they didn't agree, then you might just consider assuming they're different and running a different test. You don't have a different test right now, but you will soon. So I'm assuming these observations are independent. They're volunteer. The samples consist of volunteers, may not be independent of one another, right? Maybe family members said, hey, you should participate in this study, and you got a whole family in there. And genetically, maybe somehow, I don't know, poetry writing, so everything I say is speculative, but maybe there's something, maybe there's something there between family members that make them all better at poetry writing, and you wouldn't have a truly random sample, independent sample. But we're going to assume they're independent for now. We're going to run that step. We've already done this. We've seen this one before. You've done it in the homework. So there's the 5 steps. I rejected. We decided that there's evidence that the intrinsic group has a higher mean. So we did all that. So that was the first 5 steps. Then we will state the conclusion. There's our conclusion. I'll let you read through that, but we've done that one before. We didn't have a random sample. Can't generalize to the whole population, but it's very intriguing. We can imply causation because we had a randomized experiment. And that's how you want to do. That's how you want to go. So darn it, I really like to have a 2-hour live session. I'm sure everyone agrees with me. Maybe, maybe not. We can do this in office hours. I wanted everybody to go out and do these. The data sets for these are on Canvas. So they're on Canvas right now. There's one file that has the happiness, the mice, and the SSHA. What I'd encourage you to do on your own time is to go through, do a proc t-test on these data sets, and generate those histograms, and make your decision. Or can you assume normality? Can the central limit there kick in? Are you going to assume different standard deviations? Look at the F-test if you can assume normality, so on and so forth, and then compare them to what I have here. This is from the happiness study. This is from the mice study. And this is from the SSHA. This is another full example going through the whole thing. So I'll leave that for you. Let's do the first one, maybe the first and second. I'll leave the SSHA study for you to do on your own. So just looking at these, the happiness study, that is the histogram. If you ran them, there's the histogram right there. So don't read this yet. Question, and I can't see anybody's responses, so just somebody shout it out. Feel really confident. Does that look like there's evidence against normality? Keeping in mind, you can just count these dots. 1, 2, 3, 4, 5, 6, 7, 8. There was 8 from one and 1, 2, 3, 4, 5 from another. Small sample size. What do you think? Does it look like there's evidence against normality?
I would say yes.
Yes.
Awesome. I would say yes, too. I would say yes primarily because of this outlier. I wouldn't expect something to be this far away from whatever we think the mean is, given that we only pulled 8. Anyway, only pulled 8, I wouldn't see this. It's probably more likely that this is a left-skewed distribution. That's what this kernel distribution is right here, that red one. That's a different way to estimate a distribution, and this one's clearly estimating something that's right skewed. This one is pretty consistent with a normal distribution. But this one, both of them have to be normally distributed, so I would agree. Now what about equal standard deviations?
You said right skewed. Did you mean left skewed?
I meant left skewed. Yes, I'm sorry. Yes, left skewed here. Thank you. Yeah, I meant left skewed here. What about equal standard deviations?
They're not equal. There's more
equal.
variance in the bottom.
Great. Fantastic. I would say the same thing, but I would, the statistician lawyer in me, or the OCD, what we really need to say is that the evidence, there's strong evidence that they're not equal. We don't know for sure that they're not equal. And if we told that somebody that didn't know statistics, they would magically think that you knew something about it that we may not. So, so we don't know it, but there certainly is strong evidence that they're not equal standard deviations. So we can assume they're independent, but a t-test would not be appropriate here because we don't have large enough sample size that if this is left skewed, especially this heavy left skewed, that the means will be normal. The means will probably be left skewed as well. So not a good thing for a t-test here. How about these guys?
They look normal.
Yep.
Cool.
More normal. Yep.
Great. And so it's a hypothesis. You know, I like it. You can say they look normal, especially with bigger sample sizes. You can say they look normal. I like to stay on the extreme side. Just train myself and been trained the other way. I say there's not a lot of evidence against normality here, but certainly the bigger your sample size and the more symmetric that distribution, the more evidence that they actually are normal. So it's not a true visual hypothesis test like that. So that's fine. But certainly there's not a lot of evidence against normality. Looks like I've got pretty good sample size here. I can check out exactly what that is. But even if they're not quite coming from normal distributions, they're not too far from it. Central limit theorem should make it robust. Equal standard deviations, I think we'd all agree. Judging from the box plots and judging from the histograms, pretty significant evidence against normal standard deviations, against equal standard deviations. Pretty significant evidence against equal standard deviations. Now the next question would be, here's my sample size right here, 32 and 32. So what do you think? Don't read that equal standard deviation sentence there. Do you think I'm robust to the equal standard deviation assumption?
Yes.
Yes, I say so.
Because the sample size are the same.
Exactly. Great. We know we're robust in that situation. Now, if one was 31 and the other one was 32, still really no problem, right? They don't have to be exactly equal. If one was 100 and another one was 101, that's the gray area. You know, that there's, of course, there's some point in which you really want to stay away from that. But certainly if they're equal, then you're robust to that assumption. We are in this case robust to both assumptions. We're going to assume independence. T-test is appropriate there. I'm going to leave the SSHA one for you guys to work on. I'll kind of speed through that. There's lots to look at. Okay, there went the scope. Okay, so that is that. So that's the first part of what we want to talk about. Now I want to go into these transformations and really explain those. What do you think? Any questions on the first half? I'll take one sip. Hold on. Okay, so let's go into transformations. I also got some questions. You've seen this graphic in the book, but I think it's a great one. I think it's too great. Things don't work out exactly like this, but we do have the central limit theorem. What we're looking at here is when it might be appropriate to run, to do a log transformation. One time it's you should look, before we look at this, one instance where you might want to look at log transformations is when your data is exponentially different from each other. So if you've got like 10, 10, 10, 10, 10, 1,000, a million, you're going to be able to bring those in closer to each other. Clearly, that's heavy right skew, right? 10, 10, 10, 10, 10, 10, 1,000, a million, and 5. So that's going to be super right skewed. But if you take a log transformation, and I should say that in statistics, unless otherwise noted, LOG means log base E. I don't defend it. I don't like it. But in mathematics, it's LN. When I say log, I mean base E, unless I tell you otherwise. Everywhere else in mathematics, LOG without anything means log base 10. In statistics, LOG means log base E. So anyway, that's one instance. Another instance is this one. When you look at, this is what you would see from the sample, the side down here. This is untransformed, see, before transformation. So if what you see, if from the sample, one group, the sample with the smaller mean, right? This is the scale right here. The sample with the smaller mean, if it has also significantly smaller standard deviation than this other sample that has a higher sample mean with a bigger standard deviation, that's a good time from a log transformation. Why? Because this bar right here is the log function, right? A function is just a mapping. What do I mean by that? It maps numbers down here to the transformed axis, which is the log axis. So let's see why this one works. Notice how it goes up steeply and then levels off. So look at what that does to mappings. What that does to this one is it takes this, let's look at the lower one. It goes up and it pulls it this way. We're still at the steep part of the curve here, right? And there's different transformations that we can make in different situations. This is just for the log transformation. So the steepness of the curve is early. And since it's early, it's going to map things basically to the same width it is. It's almost like the y equals x here, right? It almost has a slope of 1. So this one's about this wide. So this one's going to be about the same width. And what it likes to do also is it makes it more normal. They're not going to be perfectly normal like they show in here. But they're going to have about, for the first one, it will be a little more normal. So some central limit theorem will help us out in either, on either side. But the standard deviation will be about the same as where you started. What's different is by the time you get out here a little bit deeper into the scale, to the greater numbers, look what happens. It stops being so steep and starts flattening out. And that's good for us because when it gets flat out here, look what it does to the mapping. Here's my smallest value, and look, my other value is way out here. I'll say it's way out here. So let's map the boundaries of this distribution. This one's going to go up and get mapped here. Now, as x gets bigger, y doesn't get as big as fast as x gets big. As x gets big here, y is going up less and less and less more extreme. So by the time you come way out here, when I come over, I've gone way out in the x, but I've only gone much smaller in the y. So here is the lower bound, here is the upper bound, and lo and behold, it really brings in the standard deviation. So I encourage you to draw that same thing and switch these. Make this the small standard deviation and this the big standard deviation, and it's going to keep this wide standard deviation. If I switch these distributions right here, it would map this one to about the same as what it is now. And it would map this one to something much smaller, which clearly wouldn't help. It would keep the big one big and shrink the small one, and it was already smaller than the big one. So it would exacerbate your problem. But if you start with the small one with the smaller mean and the big one with the bigger mean, this particular transformation will help you resolve your standard deviation issues, which is great. And the reason why we like the log transformation better than maybe a square root transformation or an x cubed transformation, right? The square root has about the same it's different, but it's about the same concavity. The reason why we like this one is because it's so interpretable. It's more interpretable than the square root transformation because I can get it to the ratio of medians on the original scale, whereas it's hard to get the square root transformation back to the original scale or any other, x cubed transformation or what have you. Okay, so let's see an example. So, but first, before we hit there's the example. Before, we want to get this, great. So in an observational study, it is estimated, so this is for a log transformation, it's estimated that the median for population X is E to the difference of the means of the log scale. I'm going to show you exactly what that means because it gets confusing when you look at it like this. But notice, this is after the transformation. After I transform the X and the Y variables, I will have a bunch of log X's and a bunch of log Y's. All right, that's what transformation is. Let's look at the X's and the Y's. Now if I take the log transformation, I have a bunch of log X's and I have a bunch of log Y's. So then I can take the mean of those log X's and the mean of those log Y's and do a t-test on the means on the log scale. That's what we're going to do, right? These are all log numbers, but they have the assumptions for the t-test. So I'll compare the mean of the log X's to the mean of the log Y's. If they're significantly different, then I can make this conclusion. All I need to do to get back to the original scale is take E to the estimated difference of means on the log scale. And that would be confusing to me to hear about, but it's much easier once I show you what that actually means. But I'm just introducing it to you now. So it's estimated that the median, not the mean, but the median of the population X is E to the difference of the means on the log scale times as large as the median for population Y. If this value turns out to be 5, that means the median of population X is assumed to be 5 times the median of the population of Y. And that's pretty interpretable. For a randomized experiment, it's estimated that the response in the experimental unit to treatment X will be E to this function times as large as its response to the treatment of Y, because in a randomized experiment, we're assuming causation. We're not just talking about the medians, we're actually talking about the units because it's causing them to be larger. Oftentimes I say it causes the median to be bigger. That's just me being conservative. In a randomized experiment, we're saying that a change in X should cause a change in Y. Okay, so you've seen this example. I love the idea of cloud seeding. We can go into the science of it, but that's for another day. What we wanted to do is on days that were deemed suitable for clouding, I assume everybody's kind of seen this example. They did a randomized, the pilots didn't even know, right? And this is back to experimental design. You want to make it double blind. You want to say, hey, pilot, you may have silver iodide or not. And why is that? Because if I'm flying around and I know I have the placebo or I know I have the not silver iodide, I'm like, this is ridiculous. This is not going to make it rain anyway. I'm just going to land early and go out to lunch. So each person had to not know what they had. Each pilot, when they were seeding these clouds, had to not know what they had on board so that they would fly the same no matter what was on board, and it would reduce the chances of bias in that respect. So anyway, we seeded some clouds. We didn't seed other clouds. And here's what we had. And measured the precipitation. So the seeded clouds had this precipitation, and the unseeded clouds had this precipitation. Problem, right? Looks like we have pretty big sample size, but probably not enough to be robust to the assumptions of normality here. I don't remember what the sample sizes were. Maybe I have that here. Don't remember what the sample sizes are. They look pretty close to being the same. So maybe the standard deviation is not as big a concern, but the normality assumption is certainly a concern for me at the moment. I need to add the assumptions to this, but I'm just looking at the transformations here. So what did I do? I did a log transformation. And I had a question on the quiz on, can you show us how to actually do the log transformation in SAS? This is it right here. You just say data cloud, that's your original data, set cloud, and then say log rain equals, and this is a function in SAS, the log of the rainfall. And that log is assumed to be log base E, even in SAS. So you take the log transformation. Now I say, okay, let's let data equal cloud. I just overwrote cloud. I just added to it. Now it's got a column called log rain. And now I'm going to do my prop t-test. I'm going to break up the two groups on the class statement. It's still treatment, right, just as it is here, class treatment. And the only reason I ran this t-test was to get the default output. I'm going to run this one to actually get the results. So now I'm saying do the variable, do it on log rain, not on rainfall. Do it on the transform variable. So that's how you do it. I encourage you to try that out in SAS. But remember now, we're still doing a t-test because we can. But we're doing a t-test on the mean of the log of the seeded and the mean of the log of the unseeded. And here we're going to get it. And I'm going to show you why this is. I probably should have done my little rigmarole here earlier. But notice this difference here, 1.1438. This 1.1438 is the mean of the log seeded minus the mean of the log unseeded. It's not on the original scale. So how do I get it back? I simply take E to that difference. E to the 1.1438, it's right here. E to the 1.1438 equals 3.1. And notice, first of all, notice that that was significantly different than 0. Because I'll ask you something real quick. If two things are equal, what is the ratio? If two things are equal, the median of seeded is equal to the median of unseeded. What is the median of seeded divided by the median of unseeded? Two things are equal. What is the ratio?
1. Assuming it's not 0. Assuming that you're not dividing by 0.
Sure. Assuming that they're not both 0.
0.
Sure. 0 divided by 0. But any median not 0, and on the log scale, it won't be. Right? No, I guess it could be. That's a good point. So yeah, if they're not 0, but this one here, so the whole point here is that when I reject, notice that's 0.0070. When I reject here, it's saying that this one is significantly different than 0. And when I take E to that, I get 3.1. So 3.1 is, of course, bigger than 1, which implies that the seeded median is bigger than the unseeded median, and by 3.1 times.
I lost your voice. I cannot hear.
Okay, can everybody hear me now?
Yeah.
Let's go back 30 seconds.
Okay. Okay. So notice here that I actually ran a one-sided test here, right? You can see that because I had infinity here. So since it's a one-sided test, my whole point here is that since it's a one-sided test, we would want to run a 90% confidence interval. We'd want to run a 90% confidence interval. A one-sided 0.05 test is equivalent to a 90% confidence interval. That's why I ran a 90% confidence interval here. You can see that alpha is 0.1. So this code here actually isn't exactly what this code here is. I should probably replace that. I have alpha equals 0.1 here. This will come up with a 90% confidence interval. And this is where I'll get 1.5 to 6.7. The confidence interval for this 3.1 is 1.5 to 6.7. Notice that the lower bound is bigger than 1, meaning that equality is not plausible. That equality is not plausible here. Okay, so that's how we want to. Let's see what's next here. So that's how we want to look at this. Again, if you run this on your own, run this code at alpha 0.1, you'll get a 90% confidence interval, and the boundaries here will be from something a little bit bigger than 0 to something bigger than 0. That's what these will be. You exponentiate these boundaries to get this. You exponentiate the lower bound and the upper bound, just like you exponentiate this to get the point estimate. You exponentiate that number and this number from a two-sided test to get the boundaries on the original scale. So let me break out of here real quick, and I'll show you why it's the ratio of medians. So why it's the ratio of medians. This is kind of a fun thing to look at. And then there's one more, you saw down there, there's one more example if you want to check that one out. So let's do it. Hey. All right, so here we go. There's a couple things we're going to need. One of them is chalk. I'm going to try to write it on here so we can all see it. Here is, I need a proposition real quick. So here is the proposition. Ask any questions you got, but I'm going to do this real quick. If I have a normal distribution, what do I know about the mean of the normal distribution and the median of the normal distribution? From the bridge course or just, what's that? That they're the same. That's right. If I have a normal distribution, the mean and the median are the same. Okay, that's proposition one. So, so what do we do? In a log transformation, the reason why we run the log transformation is because we think that the log of x is normally distributed with some mean and some standard deviation, and that the log of y is normally distributed with some mean, say mean x, and well, I'll say mean log x. That's where it gets complicated. Mean log x and mean log y with some standard deviation, but we're assuming those standard deviations are the same. So that the log of x's are normally distributed and the log of y's are normally distributed. That's our assumption when we run a t-test, or at least the means of those from the central limit theorem are normally distributed going into this. Okay. So what do I want to do here? I want to come up with another proposition. I'm going to call that proposition 1. Proposition 2 is this. Note that the log transformation is monotonically increasing. It's a monotonic function. Now what does that mean? That means that it's always increasing. It flattens out, but this keeps increasing no matter what, right? X cubed. X cubed is a monotonic transformation. This is not a monotonic transformation. It goes up and down. But this one, the log x is always increasing, which means if it's always increasing, think about what that means just mathematically. If x1 and x2, if x2 is bigger than x1, then the log of x1 or the log of x2 will be bigger than the log of x1. For any number x2 bigger than x1, the log of x2 will be bigger than the log of x1 because it's monotonic. So remember that there for just a second. That's not proposition 2. We got to just know that. So proposition 2 is this. Let me consider my x's. Here's my x's. Let's say I put them in order. x1, x2, x3, x4, and x5. This isn't really a proof, but it's a heuristic. It's a heuristic proof. A proof of concept. If these are in order, I'm saying that's the smallest one and that's the biggest one. What is the median of that data set?
X3.
X3. Great. Now let's transform them. Remember, log is a monotonic function. It's a monotonic transformation. So if I look at the log of x, I have the log of x1, the log of x2, the log of x3, the log of x4, and the log of x5. What's the median of this? Of this side?
Log x3.
Log x3. That's the median of the log of x. That's the median of the log of x3. So now given that, let's get proposition 2. Proposition 2 is the log of x3, or let's do this. The log of the median of x. If I took the log of the median of x, that would equal what? The median of x, do it like that. The median of x is x3, so the log of the median of x is the log of x3. Right? That's x3,
Yes.
That's the log of x3. The log of x3 equals the median of the log of x. So my proposition is for a monotonic, right, the log of x3, that right there, We already said that's the median of what? Of the log of x. So my proposition is that the log of the median of x for a monotonic function is equal to the median of the log of x. I can pull that median out if for monotonic functions like the log. I can switch those. The log of the median is equal to the median of the log. Okay, that's proposition 2. As usual, a million times, I never leave myself the right amount of room. Hang on a second. I'm getting stuck. Okay. All right, so those are my 2 propositions. Now let's do what we came to do. Just enough time. There we go. I'll turn it back to those propositions here in just a second. But let's look at what we're doing. What we're doing is this. Let's go just a little bit more. Okay. So what we're doing is we're looking at the difference of the log of x. What we're looking at here is the mean of the log of x minus the mean of the log of y. That is our test statistic. When we run a t-test on the log data, that's what we're doing. I'm going to call this the mean here, but that's the same as mu log x, and that's the same as mu log y. That's what I'm testing. And if that's the sample, that's x bar log x minus x bar log y. Every test we've run so far is the mean of x minus the mean of y. But now we've transformed the data. The mean of the log of x is equal to the mean of the log of y. That, or minus the mean of the log of y. That's what I'm testing. That's what that 1.14 was. So what we're going to do, well, I can't go back to that, but that's what that 1.14 is. I'm going to go, this was like the seeded. This is the mean of the seeded was 5 something. The mean of the unseeded was 3 something. And so when I subtracted them, it was like 1.14. And then we found that this was statistically significant. So let's say that this equals 1.14. Let's put little bars on this. So I go after my sample, I take the sample mean of the log of x's, I take the sample mean of the log of y's, I get 1.14. So note, remember that our assumption is that this transformed, not the mean, but it transformed the individuals, the log of x's themselves, to a normal distribution. If that's the case, then I can do this. And that's where I use proposition 1. I assumed that the log of x's were normally distributed, and I assumed that the log of y's are normally distributed after my transformation. So if that's the case, then the mean of the log of x's should be the median of the log of x's and the median of the log of y's. Fantastic. Great. Now let's use proposition 2. Ooh, we're getting good. So now I've got the median of the log of x's, but those are equal to the log of the median. I can flip this. So this is the log of the median of x minus the log of the median of y. Come around that proposition there. Notice this is on the log scale, that we've just done something awesome. This is on the log scale. What the heck is a log seeded cloud? What is a log rainfall? What is, from the seeded, what is a log? I don't know what a log rainfall is. But once I switch these from this proposition, I now have the log of something on the original scale. I know the median of x is something I can use. The median of the log of x is not something I can use. But this transformation here, now I've got this. Can I just get rid of the log? That would be nice. Remember that this is one log minus another log. And you can look this up if you don't remember it. I don't expect you to have remembered it. But if you do, that's great. When I subtract 2 logs, that's the same as the log of the ratio right? The log of A minus the log of B is the log of A over B. Now you see where the ratio of the medians come from. Well, how do I get rid of the log? I simply exponentiate it. Exactly. And that's why what this equals, right, these are equal. The log of the median of x is equal to the log of the median of this, which is equal to 1.14. Right? That's equal to 1.14. That's equal to 1.14. That's equal to 1.14. That's equal to that. So that's equal to 1.14. So when I exponentiate both of these, exponentiate both sides, I get the median of x on the original scale divided by the median of y on the original scale, something that's very interpretable, which is why we love the log transformation, is equal to simply e to the 1.14, which equals, in this case, 3.1. So my best estimate is that the median of the seeded, for this one, the median of the seeded rainfall is 3 times that of the median of the unseeded. That's really good evidence for people selling silver iodide. Now be careful, right? Because up here, this 1.14, this was a t-test. I can get a 2-sided confidence interval for this 1.14. And I'm telling you that that's going to be something a little bit less than 1.4. So let's come down here and say the confidence interval on the log scale was, I'm just making this up just for the sake of stuff. Let's say that that's 1.10, so that's a margin of error of 0.3. This is going to be a really narrow interval, but that's a margin of error of 0.3, so this is 1.17. So I'm not sure it's 1.14. I just made these up. They're not going to match what I had on the slide. But for all intents and purposes, I don't know that it's 1.14. That's my best guess. Given the data, I'm 90% confident, or however confident, that it's in here. Well, all you have to do is, if you have the confidence interval for this guy, exponentiate both sides, e to the 1.10, e to the 1.17, and then you have a confidence interval for the 3.31. Right? Just for completeness, we'll go ahead and do that. So second e to the 1.1 is 3.0, to second e to the 1.17 is 3.2. So I just, again, in case you're watching this video again, I just made these up just so I can make an example. Yeah, remember the real one was like 1 to 6, or 1 point something to 6. But that's how you do it. You look at the confidence interval on the log scale, and the difference of the mean to the log scale. Take a confidence interval, exponentiate the point estimate and the lower and upper bound, and you get something back on the original scale, which is so useful, which is why we love the log transformation when possible. That's why it's so popular. Yeah, Ramesh.
Yeah. Can you hear me?
I can.
Okay, thank you. Hey, I do understand, in the symmetric distribution, we have mean equal to median. I understand the math of transformation, log transformation, and exponential stuff. But I still didn't get it, why we have to use median instead of mean.
The median instead of the mean?
Right. We do, we are saying mean equal to median, and we converted, we transformed mean values into median. We did all the math, but why do we have to use median instead of mean?
You've got to use the median instead of the mean because of Proposition 2. Because median deals with order, and the mean does not. So I can find you an instance where the log of the mean of x does not equal the mean of the log of x. Because we're dealing with order here, we know that the log of the median of the log of x. We're not sure that the log of the mean of x will equal the mean of the log of x. I'd have to come up with an example for you, but I can find a counterexample because the mean isn't the middle value.
Right. Okay.
So yeah, I'll I encourage you to work on a counterexample if you want to. That's a good question. If I get some time, I'll try to look at a counterexample for that. That should be pretty easy to find, though. But yeah, that's why we have to go to the median, because that one's always true.
Are we also doing it because of robustness of the median relative to the mean? Where the mean will shift if I have outliers where the median stays constant?
Yeah, I'm sorry, say that one time. Oh, but yeah, well, I'm just thinking of one right now, sure. On the X scale, remember, we're thinking this could be any distribution. If this is right skewed, right? If this one's right skewed, then the mean will be a bigger value. The mean could be bigger. Actually, the mean doesn't even have to be one of these values. And I guess the median doesn't either if there's an even number. But the mean could be bigger than X4. To your point exactly, if X5 is a huge outlier, the mean will be bigger than X4. But these guys are supposed to be normally distributed. And so the mean will be somewhere around X3. The mean should be somewhere around in the middle. So the log of the mean of X3 will be like the log of something bigger than X4. But the median of the log of X will be something around X3. Or something around log X3. Sorry, this one will be something around log of X4. This one will be something around the log of X3. And so they don't have to be equal. And that whole comes from the fact that we think we know, under our assumptions, we know the distribution of the log of X, that it's normal. This could be any distribution.
Okay, so basically we are saying the mean values are variable. I mean, there is a variance in mean values, but median stays the same. So that's the reason we will use median.
I think so.
Okay, so what we are
saying
saying
what
is,
you said?
right, what we are saying is the mean values are variable in the sense like, there is a variance between the mean values. The median value on both scales is pretty much, it's going to be the same. So that's why we kind of convert into median and then we convert back into the actual value.
Sure. Yeah, I don't know if I'd use the word variance, but yeah, the mean can be anywhere along the distribution.
Right.
The mean can be close to the biggest value in the distribution. But the median, I guess that's what I'm saying. Yeah, the mean could be the 90th percentile, but the median is always the 50th percentile.
Okay. I think I got it. Thank you.
Cool. Yeah, that's a good way to think about it. The mean could be the 99th percentile, but the median will always be the 50th percentile. So the log, if this is the mean, this would be the log of the 99th percentile. Some huge number doesn't have to be equal to the median or to the mean of the log of X, because the mean of the log of X will always be close to here because we think the log of X's, or this is the mean, the mean of the log of X's is the same as the median of the log of X's because we're assuming the log of X's are normally distributed. So this should be somewhere around the 50th percentile, whereas this would be the log of the 99th percentile. We could pick a value. So cool. Let me look at the rest of this guy real quick, but share. Here's another full example using data that you may have seen in the homeworks. I forget if I give you this one or not. I think I might have. There's like fired and not fired. This is a similar data set. But anyhow, state the problem, check the assumptions, go through it. So there's another full example to check out. I don't think that one was a log transformation though. But there is, if you want, again, so I guess I've reached the end of the internet for those. I did have a question about the power of a two-sample test. So I didn't get to that in this live session. That's one thing that we didn't get to. I will address that. Whoever had that question, if they want to just post it to the wall or come to office hours, I can certainly address it there. Or hopefully everybody's met Nibrat, but he is back in town and on doing an office hour. So he's a great resource. I forgot, he either has his office hours. Does anybody know when his office hours are? He said he was going to announce it to everybody.
and didn't announce it to me. It's like Tuesday or Wednesday.
Yeah, it was Tuesdays at like 2 or
6 to 7.
3, or 6 to
Tuesday
7,
about 6
yeah.
to 7.
Tuesday,
Yeah,
6 to
that
7.
sounds right.
But you can check out his office hours. I want to give a shout out and a commercial to his, and of course mine are at, when are mine? At 6:30 to 7:30 on Sunday. 6:30 to 7:30 on Sunday, and we can iron out the rest of that. But get started or finish up that homework, and we will have a rip-roaring good time. What do you guys think? We got time for any questions here. That was on assumptions. That's Unit 3. I think we covered them pretty thoroughly. We got to log transformations and covered that pretty thoroughly. We could have probably squeaked in one more example, but you should be prepared for the homework. Yeah. Does the transformation function always have to be monotonic positively? Can it be negative? In other words, is it the case as long as it's just in one direction?
Well, I mean, it doesn't to have proposition 2, to have the property of proposition 2, it doesn't. But the nice thing about the log, we didn't choose the log because it was monotonic, because there's lots of monotonic functions. The square root function, the x cubed function, it had to be monotonic for it to work, but we didn't choose it because it was monotonic. We chose it because
it was reciprocal?
Exactly, because it has this property, right? Because the log of x minus the log of y is the log of x over y. That's what got us back to our original, That's what got us back to our original scale. And that's why we like the logs. It's so easy to get back to something that's interpretable on the original scale, right? The log of the median is not helpful, but the log, the log of the median of, the median of the log of x is still on the log scale. I don't like that.
Sure.
But the log of the median minus the log of the median, I can do the log over the median over the median of x over the median of y. I can exponentiate that and get rid of the logs, and I'm left with the original scale. And that's not possible with the square root function or with the, it's possible with the square root function, but you end up with like the square root of x and the square root of y, and you have to start interpreting things on weird scales that don't necessarily make sense. But this one's nice. But yeah, but you certainly could, but you just end up with maybe in a result that's not as interpretable as this one is.
Thank you.
No problem. And I also got this in the quiz. When do we use a log transformation? And we came up with a couple. I think it says in the book, if some of your values are exponentially larger than others, that log transformation will help reel them in. So you don't have these big right skewed distributions. It'll bring them in. I showed you an example where if you have the sample mean of the smaller group, the sample standard deviation of the smaller mean, and the one with the bigger mean has the bigger standard deviation, a log transformation might work there. My experience is that a log transformation is not hard to try. So when you have it, just try it. Just transform it and look at it real quick. And you'll be surprised. This different data has different features that you might try to put it all under an umbrella, but it's really easy to check. We're going to do log transformations this semester when we hit regression. So we're not going to get away from it. It's going to actually start building on this. And they become really helpful because we also have a normality assumption in regression. And the log transformations are going to help us be robust to that. Actually, it's going to help us be that, so we don't have to be robust to that. And it's got the same interpretability. There's the same really good interpretation on the log scale. Whew. So, hooray. So awesome. So, wow, took to Unit 3, but we didn't have, I forgot what happened in Unit 1, but that was awful. In Unit 2, the power went out, so we had to do a couple extra sessions. This one's been pretty smooth. I'm impressed. I'm happy. So we should expect this. You should always expect this, but I'm glad we got
Knock on wood.
Yeah. We're good.
Nice. Nice, Max. We had the same one. Okay, well, I'm good. I got to do the 6372, which you guys will be taking next semester. We're doing two-way ANOVAs. We'll do one-way ANOVA here in 2 chapters. Unit 5, we'll do the one-way ANOVA. We do two-way ANOVAs in the second one. So you got to look forward to that. And but that's it for today. That's Unit 3, and that's a ton. That's a ton. So great work.
Thank you.
My pleasure. We revved up for a Thursday night whammo. I'm gonna throw it out there. I forgot did I lose it last time? Yeah, let me try this. Let's go third column, second row. Okay, third column, second row is Priyanka. Will you break us out? This would be awesome. Oh, sweet. She's getting on audio. Great job, you guys. Unit 3 in the books.
Okay, so 1, 2, 3.
All right. Nice enthusiasm. Great work, guys. I'll see you Sunday or next Thursday, or I'll talk to you before then.